Now, hello again. Are there any questions so far? Well, no questions. I could continue to another step. As I have promised, I will put some light, shed some light on the constant k. Now, we know that k squared is equivalent to this equation, minus j omega mu times j omega epsilon plus sigma, where omega is the angular frequency, that is 2 pi f, j is the imaginary unity, mu is permeability, epsilon is permittivity, and sigma is conductivity, specific conductivity of the material. Now we will get to somehow establish beta and alpha out of this equation, which means we have to carry out the square root and find out the real and imaginary part of the square root of this equation. I will carry out that for you easily in the next step. So the result of that would be beta, as you remember, it affects the phase of the propagating wave, is equivalent to omega, that's the angular frequency, times the square root of, and within this square root we have mu epsilon divided by 2 times a bracket within which we have a square root of 1 plus so I will try to read it. Beta is equivalent to omega times a square root of, and now within that square root we have mu epsilon divided by 2 times, within brackets, again a square root. The argument of that square root is 1 plus sigma over omega epsilon, and this fraction is squared, end of the square root, plus 1, end of the bracket, and all the square roots. Not very nice to remember. Now I have to give you the alpha. Surprisingly, out of the complex arithmetics, those two equations are very, very similar. They only differ in this point where for alpha there is minus. So I will put it down now. And that's it. Now, if I may, I would make 2 remarks. First remark, a dangerous kind of mistakes. You should still remember that mu and epsilon is mostly given as relative values. So, for example, I will tell you calculate the wavelength within a glass which has the relative permittivity of 4, but that means that the permittivity is the permittivity of vacuum times 4, and you still have to put there epsilon 0 times 4, the same for permeability. So don't mix relative and absolute values of permittivity and permeability. That's the first point, just not to make mistakes. But then there is a second point, and that's much more interesting. We have here something. It's a fraction. We will shortly learn that it is an important fraction, but what the fraction represents, there is sigma over omega epsilon. And sigma is conductivity, specific conductivity of the material. And omega epsilon, what that is? Well, remember that with increasing frequency, there is increasing angular frequency, omega, and it also means that the displacement current within a dielectrics increases because those two, let's say, poles of polarization interchange their places more frequently. So you have more charge passing any cross-section within a time unit. So the displacement current is more and more important with increasing frequency. It has no importance in electrostatics. It gets more and more importance with increasing frequency. So this ratio, more or less, is a comparison between conductive current and the displacement current. Having said that, we now should focus on some simplification of those two nice but complicated formulas. And those simplifications can allow us to make simpler calculations within specific cases. To get it physically grounded, we would possibly investigate first two kinds of materials. One of them is called dielectrics. Well, within electrostatics, the definition of a dielectrics was it has no conductivity, then it is dielectrics. Well, within here we can define it in a different manner, and this is important. We have here something sigma over omega epsilon squared that we add to 1. In which cases we'll be able to neglect this term? Well, in those cases where sigma over omega epsilon is much less than 1. Then you square it, it's much less than 1, and you can neglect it. So for cases where sigma over omega epsilon is much less than 1, we can call the material dielectrics. Dielectrics, and in that case this whole equation simplifies a lot, because if this is very small, its square root is much smaller, and we get after all a square root of 1, which is 1. We can add that to this one, to this unity, we get 2. We can then cancel this 2 against 2 in denominator here, and all we have obtained is beta is equivalent to omega times a square root of mu epsilon. So for dielectrics we have a simple equation for the phase propagation constant, which is beta is equivalent to omega square root of mu epsilon. And now again for the alpha, for the damping constant. Sigma over omega epsilon is very small, raised to second power is even much smaller, so it will not change unity very much. We can consider that this is 1. Subtract 1, we got 0. So the result is that alpha, the damping constant, is 0. And our conclusion is, whenever we can neglect conductivity, we get 0 damping and the wave propagates without damping. So we've got, for dielectrics, we've got beta equivalent to this equation and alpha is 0. Now let us switch to other important kind of materials we have already encountered within electrostatics or steady current field, that is conductors. Within conductors, conductivity is very high. Once this fraction gets much bigger than 1, and that is when sigma is much bigger than omega epsilon, and that is when conduction current highly prevails over displacement current, we will have a conductor. And within this case, we can again somehow simplify the full equation. So that if we have sigma over omega epsilon much bigger than 1, we raise it to second power, then we can neglect this one. A square root of a second power is the original fraction, which is much bigger than unity, so we can neglect this unity, and we obtain an equation that tells us that beta is omega a square root of mu epsilon divided by 2 times sigma over omega epsilon now epsilon, the permittivity cancels, and we can get this omega from outside of the square root inside. So if we move it here, we get omega squared. We cancel against omega in denominator, and our final result would be that the beta is a square root of mu sigma omega divided by 2. And at the same time, we have got alpha. And remember, we have neglected this unity within the simplification. So it makes no sense whether there is +1 or -1, the result would be the same. So for good conductors, the real and the imaginary part of the propagation constant are exactly the same. Now, a good lecture is a lecture when there is a surprise. Something that changes our point of view we had before. And as we are arriving to the end of the lecture, I have to reveal the surprise for you. When we have been talking electrostatics, I told things like, we have dielectrics like paper, wood. We have conductors like copper, steel, aluminium. But from the standpoint of an electromagnetic wave, this is not perfect. Well, we have dielectrics, and a dielectrics is a material that behaves like a dielectrics if and only if the conduction current is much smaller than displacement current. So sigma is much less than omega epsilon. But omega has inside 2 pi frequency. And now you can get to a strange result. That is, the same material could behave at some frequencies as a good conductor. Because at low frequencies there is no displacement current. For example, seawater at low frequencies, like long and medium electromagnetic waves used for radio transmission, seawater behaves like a good conductor, and it reflects the waves up, so that if you have a transmitter, seawater, and a receiver, well, you can get a direct ray going from between those two antennas and an additional amount of reflected power from the seawater, so that you can even get twice the power at the receiver. But if you increase the frequency, then the displacement current gets bigger and bigger. And at frequencies that are high enough, it happens that the displacement current is much bigger than conduction current. And the result of that is a change of behavior. Now the seawater behaves like a dielectrics. And this happens with plenty of materials. So first we have been talking about conductors, like we know that this material is a conductor, dot. But now we have learned that for many materials it depends whether the conductor behaves like a conductor, the material behaves like a conductor, and it depends on the frequency. For example, human body, for low frequencies, excellent conductor, around unities of gigahertz, lossy dielectric, at hundreds of gigahertz or terahertz, dielectrics. That is something that changes our point of view. So whether something could be considered a dielectric does not depend purely on the material, but it depends on its properties and frequency. And we can distinguish that by a ratio between conductive and displacement current. If the conductive current could be neglected, we call the material dielectrics. If the displacement current could be neglected, we call that material conductor. And now your questions, please. Well, if there were no questions, I will add one more trick, and this trick is about something which is called wavelength. What a wavelength is. Well, if you could freeze a wave and walk around it, you would notice that the wave, which is harmonic, repeats, the wave pattern repeats after a certain length. Well, why? Well, because because the wave has this character. If it's not damped, it is given by e raised to minus g beta z. And you know that according to Euler's equation, this could be decomposed into cosine beta z plus j sine beta z, and both that functions are periodic, so that we can establish the period of that function, which is called wavelength. So wavelength is such a distance at which beta z gets to 2 pi, because that's the period of sine or cosine. So we now know that a wavelength is such a length where beta length is 2 pi. So we can put it into a formula. Calling a wavelength lambda, we know that it must hold that beta lambda is equivalent to 2 pi. And out of that, we can easily extract lambda as 2 pi over beta. This is an important formula that allows us for establishing a wavelength within a material for a wave of given frequency. Now, it is known that for dielectrics, for example, we can easily find out the wavelength using permittivity. But it is important to know that this only holds for dielectrics. Once the conductive and displacement currents are comparable, we would have to use the full equation to find out beta and then the wavelength. So generally, once losses are present, the wavelength is shortened. And I have a second comment which is also quite important for some technologies. Let's again return back to the equation of propagation of a plane harmonic wave decomposed into the phase part and the magnitude part. So we have the term e raised to minus alpha z, the exponential governing damping, and you may find out that this is something that damps the wave, and within good conductors we have the equation for alpha. It is here. So it depends on permeability, conductivity, and omega. But the whole thing is under a square root, which means that if you raise the frequency twice, this damping only is raised a square root of 2 times. Why I tell it here? Well, the result is that if you increase the frequency, you can get to a bound where thin conductors would become transparent. Well, this is a good luck. For example, you can make glasses that protect eyes against microwave oven radiation. You just put a monoatomal layer of gold on a glass, At high frequencies like light, you can watch through that glasses, but at low frequencies it damps significantly the wave and protects the eye of the observer. Very nice. But on the other hand, it may constitute a significant obstacle to handle high frequencies, because at frequencies high enough you have to make the circuits small enough. Remember, you have to somehow get under 1/12 of the wavelength to get a lumped circuit without the effects of propagation. And now at high frequencies, that would mean that the metallic parts would be so tiny that the wave would not attenuate, penetrating through them, and even a piece of gold would not work as a conductor. And in that case, you will not be able to make a transmission line, and you have to switch to other technologies. For example, like optical fibers. At those frequencies, it would be difficult to create two conductors carrying out the signal. It is possible to carry the signal through an optical fiber, but the physics behind that is a bit different. Ladies and gentlemen, we have arrived to the end of today's lecture. We have done a big piece of job. I understand that electromagnetic waves are something which is at the first sight difficult to understand. But we will handle waves for some time within this term, and you can get used to that. So it is finally manageable, and you may understand that. So don't be frightened at the beginning. That's the first point. The second point, please remember that next Tuesday is a public holiday here in Czech Republic. So we will have no lecture next Tuesday. But I am looking forward to meet you again in 2 weeks on Tuesday in regular time. Now I will have the consultation time on Monday, because Monday is not a public holiday, and that's possibly from organization point of view all I have for you this week. But I would like to ask you for questions, whether you have any. Just what shall we do next? We have learned that there is an electromagnetic wave. It's something possibly strange for you. So we will make some examples. We will find out, for example, how the wave propagates through a media. We will learn how to calculate the wave propagation on an example of, for example, a microwave oven and a piece of meat. We will calculate the properties, the wavelength. We will also realize that for some kind of lossy materials or conductors, there is something which is called a depth of penetration, that the wave never gets fully into the volume. We will then establish why you have to cut food given into the microwave oven to some slices, why a big loaf of bread would never get heated adequately there, and why microwave oven works faster than an originally radiating oven. And we shall see how much shall we do next time, but anyway, we will do examples of electromagnetics. Also, after the next lecture, we will be able to understand all the quantities that are related to safety in electromagnetism, so that I will devote a part of the next lecture to important questions of safety, because you as electrical engineers will be certainly approached by people asking many questions. And you should know that electromagnetics, well, it's not easy for you, but you will learn that. But ordinary people do not understand that. They can't sense it, but they are afraid of it. So we have many problems, for example, with introducing 5G networks. People are afraid of that. Some of them think that that's the reason for coronavirus. One of our professors just last week had made a measurement uh, at Prague at Náměstí Míru, just on the ground under the transmitter. And he has found out that the field there is 1000 times below safety limits. And 1000 times is quite enough. So people who are not afraid of sunlight, which is 10 billion times stronger than this radiation, at least 10 billion times stronger, are very afraid of electromagnetic fields in other cases. And unfortunately, some people use that to make profit. So I would like to tell you some important aspects on electromagnetic safety, because electromagnetic field can be dangerous, but it's important to know when it is dangerous and when not. And that is also something I will tell you within the next lecture in its second part. So I have now promised you the topics for the next lecture. We both know that we will not meet in 2 weeks, but we will meet after 2 weeks on Tuesday. It will be the 24th of November. And since then, I wish you good luck. I would like to thank you for presence at this lecture and hope to meet you again then. Bye bye.
Bye. See
Thank you. Bye.